Scene script. Have you ever wondered about the mystery of the fourth dimension? What if we told you that we live in a four-dimensional world every day? Intriguing, isn't it? Dive with us into the enigma of the fourth dimension, an enthralling topic that weaves together the threads of physics, mathematics, and philosophy. Let's start with a concept you might be familiar with: time. You see, in the realm of physics, specifically Einstein's theory of general relativity, time is considered as the fourth dimension. Picture this: our universe is a grand tapestry woven on a four-dimensional loom. The threads, representing the dimensions, intertwine to create the fabric of our reality. 3 of these threads signify space: length, width, and height. The fourth, somewhat elusive thread, represents time. But what does it mean to perceive time as a dimension? Well, understanding time as a dimension opens a Pandora's box of intriguing questions. It forces us to reevaluate our perception of time. Is it a river, flowing unidirectionally from the past to the future? Or is it an ocean, with the past, present, and future coexisting like waves on its vast expanse? This concept also makes us ponder over the connection between time and the spatial dimensions. How are they linked? What happens if we move faster or slower through space? Does it affect how we move through time? If you've heard of the famous twin paradox, you know the answer is a resounding yes. Grasping these ideas might seem like trying to catch smoke with bare hands. But that's the beauty of delving into the mysteries of the universe. It challenges our understanding, pushes our boundaries, and encourages us to look beyond the obvious. So time, as we perceive it, might just be our fourth dimension. But is that all there is to the story? While time is a fascinating contender, there are theories that propose the existence of extra-spatial dimensions. Imagine dimensions beyond the familiar 3: length, width, and height. It's a concept that might seem like it's been plucked straight from the pages of a science fiction novel, but it's a topic that's actively discussed in the world of theoretical physics. String theory, for example, suggests that our universe may contain more than just the 3 spatial dimensions we're familiar with. This framework posits that the fundamental particles in our universe aren't point-like but rather tiny, one-dimensional strings. But here's where things get really interesting. For the math of string theory to work, there need to be extra dimensions, as many as 7 additional dimensions in fact. You might ask, if these extra dimensions exist, where are they? Why can't we see or experience them? One theory is that these additional dimensions are compactified or curled up, at scales so minuscule they're beyond our ability to detect. To visualize this, imagine a tightrope from a distance. It appears one-dimensional, a simple line. But get closer and you realize it's actually 3-dimensional with length, width, and a curled-up dimension, its circumference. This is a simplified analogy of how extra dimensions might be hidden from our perception. It's not just string theory that postulates extra dimensions. There are other theoretical frameworks like brane world scenarios that also propose the existence of additional spatial dimensions. These theories suggest that our familiar 3-dimensional world might be a brane or membrane floating in a higher dimensional space. These ideas are yet to be proven and remain a topic of ongoing research and speculation. But if true, they could provide answers to some of the most profound questions in physics, such as the nature of dark matter and the unification of quantum mechanics and gravity. So, these extra dimensions, if they exist, could be hidden from us, waiting to be discovered. As we delve deeper into the mysteries of the universe, we might just find that reality is far more complex and fascinating than we ever imagined. Opening. The fourth dimension isn't just about physics and math, it also stirs up some deep philosophical questions. Let's delve into the world of philosophy. The idea of a fourth dimension not only challenges our scientific understanding but also forces us to question our perception of reality. Is our reality merely a 3-dimensional slice of a multi-dimensional universe? Or are we capable of experiencing more dimensions than we're currently aware of? These are the questions that philosophers and thinkers grapple with. The concept of time as a dimension introduces an interesting debate about the nature of time. Is time an absolute entity that exists independently of us? Or is it a subjective experience, something we perceive and construct in our minds? Some philosophers argue that time is absolute, an unchanging stream that flows independently of human consciousness. Others, however, propose that time is subjective, a product of our consciousness. They contend that without conscious beings to experience it, time would not exist. A related question is the directionality of time. Why does time seem to move in one direction from the past to the future? Why can't we remember the future or change the past? This concept, known as the arrow of time, is another intriguing element of the fourth dimension mystery. The fourth dimension also challenges our understanding of causality, the idea that causes precede effects. If time is a dimension that we can potentially move through, just like space, then the conventional notion of cause and effect may need to be reassessed. Could there be situations where effects precede their causes? This is a radical and mind-bending proposition, but one that cannot be completely ruled out in a universe where higher dimensions exist. These philosophical implications of the fourth dimension underscore the profound mystery of our universe. They invite us to question the nature of reality, the flow of time, and our own perception of the world. As we delve deeper into understanding the fourth dimension, we are not just exploring new scientific frontiers but also pushing the boundaries of philosophical thought. Closing, the fourth dimension, then, challenges our understanding of reality and our place within it. One of the biggest challenges with the fourth dimension? Visualizing it. Our human minds are wired to perceive the world in three dimensions. Length, width, and height make up the spatial world as we know it. But how do we visualize a fourth dimension that our senses can't perceive directly? The concept of a fourth dimension, be it of time or space, pushes the boundaries of our comprehension. We can't physically see or touch it, so how can we possibly visualize it? The answer lies in the realm of mathematics and analogies. Mathematicians have developed models to illustrate the concept of higher dimensions. One of the most famous is the tesseract, a four-dimensional analog of a cube. Just as a three-dimensional cube can be unfolded into a two-dimensional square, a four-dimensional tesseract can be unfolded into a three-dimensional cube. But remember, these are merely representations, a way to map the uncharted territory of the fourth dimension onto our three-dimensional understanding. Analogies also play a crucial role in visualizing the fourth dimension. Take a piece of paper, for example. To a two-dimensional being living in the paper, the world consists of length and width. If we, as three-dimensional beings, were to pass a sphere through their world, the two-dimensional beings would perceive it as a series of expanding and contracting circles. They can't perceive the full sphere because they lack the third dimension. In a similar way, we might perceive higher dimensional phenomena in our three-dimensional world as strange, inexplicable transformations. But let's be clear. These mathematical models and analogies are not the fourth dimension itself. They are tools, bridges to help our three-dimensional minds grapple with the concept of a fourth dimension. They enable us to gain insights and construct theories about a realm that is inherently beyond our sensory perception. While it's not easy to imagine, the fourth dimension is a concept that stretches our understanding of the world. It invites us to think beyond our physical constraints and to explore the mysteries of the universe that are both fascinating and confounding. The fourth dimension also plays a critical role in one of the biggest mysteries of physics: quantum gravity. Quantum gravity is the attempt to explain how gravity works on the tiniest scales. Now, why is this important? Well, it's because gravity is something of an oddball in our current understanding of physics. On one hand, we have Einstein's theory of general relativity, which describes gravity beautifully on a large scale. Think planets, stars, galaxies. But then, on the other hand, we have quantum mechanics, the theory that explains the behavior of particles on the smallest scales, electrons, quarks, and the like. And here's the kicker. These two theories, as successful as they are in their respective realms, don't play nicely together. General relativity paints a picture of gravity as the warping of space-time caused by mass and energy. It's a smooth, continuous fabric, if you will. Quantum mechanics, however, describes the world in terms of discrete or quantized units. It's more of a pixelated image. The fourth dimension of time is integral to this conundrum. You see, general relativity has already woven time into the fabric of space-time, making it inseparable from our three spatial dimensions. But how time fits into the quantum world is still a puzzle. The challenge, then, is to develop a unified theory of quantum gravity that can marry these two seemingly incompatible views of the universe. It's about finding a way to describe gravity that works just as well for stars and galaxies as it does for atoms and particles. And that, dear listener, is no small feat. So the fourth dimension might just hold the key to uniting the world of the very large and the very small. It's a tantalizing prospect, and one that continues to inspire physicists in their quest to uncover the ultimate truths of our universe.